Hey class, welcome to lab number 1 of your engineering thermodynamics course, and this lab will be based on the Rankine cycle steam vapor power plant demonstration unit. My name is Richard Bernard and I will be the demonstrator for this lab. Now let's jump right into things. Now on page 2 of your lab scripts, you would notice that there are 3 main objectives. The first is to study the steam power plant apparatus and identify the main features and components. The second is to draw a schematic of the thermodynamic cycle. And the third, we want to operate the plant and record the following data after steady state condition is achieved. Now steady state means that all the variables are constant in time. Now some of the parameters we would want to record are the turbine inlet pressure, the turbine inlet temperature, the turbine outlet pressure, the volumetric flow rate of the fuel, the generator voltage, and last but not least, the generator amperage. Now we would want to identify the main components on the lab apparatus. I apologize for the quality of the photo, as you would see on page 3 of your lab scripts, but we would do one better. We would go on the actual lab equipment and point out these main components. Point out the main components of the laboratory equipment. So this big green section here is the boiler, right? Then this gauge here is the boiler pressure gauge, right? On the side here we have the fuel supply, which is regular cooking LPG gas, right? From this gauge we have the throttling valve or the steam admission valve, right? This component here is the turbine, the single stage axial flow turbine. We have a generator, AC/DC generator, right? This component here is the condensing tower. We also have the burner. We have some instrumentation on the outside here. This is a DC voltmeter and a DC ammeter for voltage and current respectively. This here is the master switch for the equipment. We have the burner switch. We have the load switch. The load rheostat that adjusts the load to the turbine. Now this entire machinery is connected to this computer, which has a software that detects and measures all the thermodynamic properties of the system, including the boiler pressure, the turbine inlet pressure, turbine outlet pressure, the boiler temperature, the turbine inlet temperature, the turbine outlet temperature, the current, the voltage, the turbine RPM, and the fuel. We could direct our focus to figure 2, which is a schematic of the actual Rankine cycle lab apparatus. So, one thing to note before we begin is that the laboratory equipment is not fully representative of the ideal or actual Rankine cycle, and we would understand a little more as we discuss further. So, as you remember from the previous video, the first thing we have is the boiler, which was the green piece of equipment, right? And in the boiler, we have water, which is the working fluid. Now, why do we choose water as the working fluid? Well, number one is not toxic, it's not reactive, it's abundant, it's low cost, and most importantly, it has great thermodynamic properties, right? This is a steam cycle, so how would we produce steam? Well, first by obviously heating up the water in the boiler, right, beyond the boiling temperature, and steam will be produced. Now, as you may remember from the previous video, the fuel we combusted or burnt to produce the heat was regular cooking gas, LPG, liquid petroleum gas, right? And this was able to heat the water in the boiler to produce steam. Now, exiting the boiler at the boiler's outlet, right, we have steam at stage 1. Now, the steam at stage 1 is what we call Trisaturated steam, right? Now, one thing to note is that in typical Rankine cycles, the steam exiting the boiler is usually in the superheated region. and I would touch a little more on this as we proceed. But this steam in this lab apparatus, this lab cycle, is dry saturated, right? Now to bring it to the superheated condition, we have this manual throttling valve or the steam admission valve. And by throttling the steam from 1 to 2, that reduces the pressure of the steam while bringing it to the superheated condition. So the steam at 2, which is the steam entering the turbine at the turbine inlet, this steam is superheated, right, at a lower pressure than at 1. Right? Now this steam enters the turbine inlet, right, and produces mechanical work. Mechanical work in the sense that the turbine blades begin to rotate. Now these blades are directly coupled to the shaft of the generator, and this rotation causes the generator to rotate as well, which produces a power output, voltage and the current, right? So that's basically how electricity is produced. If you scale a system up, in power plants, right, the rotational turbine blades are coupled to large generators, and the rotation of these blades causes the generator to rotate, which produces a power output. Now you'll learn more about generators in your electrical course, but exiting the turbine, exiting the turbine at the turbine outlet, right, the steam from 2 to 3, you also have a reduction in pressure, right, but the steam is still superheated exiting the turbine. Now this steam makes its way to the condenser, where the exhaust steam is released to the atmosphere as 4, released to the atmosphere. Now as this steam is released to the atmosphere, right, this is what you refer to as an open cycle, right? Now in typical plant applications, right, this condensate is actually collected, right? So we collect this condensate and condense it back to the liquid state, and there's usually a pump from the condenser here that pumps this condensate all the way back up to the boiler. Right now, this condensate is reused in the boiler to repeat any process. Now this helps improve the overall efficiency of the cycle, thermal efficiency, and that's why this is usually done on larger plant applications. However, if you look on page 5 of your lab scripts, you would see that due to this ultra small scale of this apparatus, the returning of this condensate back to the boiler is quite impractical, which is why it's not done in this cycle, in this lab apparatus, and the condensate is released to the atmosphere in the gaseous form, right? So now that you understand, the basic operation of the Rankine cycle and the flow through the major components, the boiler, the throttling valve, the turbine, and the condenser, right? We could represent this entire system on what you call a TS diagram. If you direct our focus to figure 3, which is the TS diagram for the laboratory Rankine cycle, right? Now, as I previously mentioned, and I keep reiterating, this cycle is not representative of an ideal or typical Rankine cycle, and I'll explain why briefly. Now, before we get to that, I will just go through each stage on top in the schematic as it relates to this chart. Right? Now, in the boiler, right, there's water, right, which is a liquid. Now on this chart, we have 3 main regions. We have a wet phase or a subcooled stage, right, which is to the left here. Within this region, within the constraints of these lines, we have a 2-phase region, which basically means that we have both a liquid phase and a gaseous state, or a vapor phase, right, are 2 phases where the liquid is undergoing a change in state to the vapor as it passes across here. Now to the right of this graph, this main graph, we have the superheated region, right? Now this is the typical shape of these TS diagrams, right? And this point, the apex of this graph, is usually called the critical point. Now this line to the right of the critical point is often referred to as the saturated vapor line, and to the left of the critical point is the saturated liquid line, right? Now that's important to remember, right? Now let's just track back a little bit, go back to the start of the process, which is the working fluid in the liquid state, right? So on a typical Rankine cycle, as you would see when you do your additional research to produce your lab report, you would notice that the liquid, the first part, begins in the wet region, in the liquid region, right, which is the water. And as you apply heat to the water, the temperature begins to rise as expected until we get to this point where we can begin the change of phase, right, from the liquid to the gaseous state. So in these sample values here, we see at around 170 degrees Celsius, the water in the boiler begins to go about a changing state from a liquid to the vapor stage. So at 170 degrees Celsius and 7.93 bar in this cycle, these are some just estimated values, some sample values. At these conditions, right, the water in the boiler begins to change state from liquid to vapor. So this happens at a constant process, and you can see the flow of the arrow, right? A constant pressure. This is the pressure line. These are the pressure lines, right? And at this constant pressure, this is considered an isobaric process, right? Now this graph shows that the water, the steam exiting the boiler at 1 is on the saturated vapor line, right? Now in actual plant applications, the steam exiting the boiler, as I previously mentioned, is usually in the superheated region. So as you do your research on the Rankine cycle, you would notice that the steam exiting the boiler is in the superheated region around here, right? So that is one reason, one region, or one point as to why this lab apparatus is not fully representative of the actual Rankine cycle applications, right? So this steam here at 1 is on the saturated vapor line and is not in the superheated region. Now to bring it to the superheated condition before it passes through the turbine, that's why we have this throttling valve, right? And as I previously mentioned, the throttling valve, the pressure is reduced, so you can see these sample values from 7.93 bar to around 1.5 bar, right, in the superheated region. So that is what you see in here on this line here as you observe the flow of the arrows. So from 1 to 2 across the throttling valve, this process, you get superheated steam entering the turbine. From 2 to 3, we also have a reduction in pressure, right? But the steam flows through the turbine from 2 to 3, right? Now from 3 to 4, this is the condenser phase, right? Now 3 to 4 really takes place in the atmosphere as it's an open cycle. So as we go back to the schematic here, the steam is exhausted to the atmosphere, right? And heat is lost to the atmosphere, right? So from 3 to 4, what this is showing is another isobaric process, right? Whereby the steam exiting the turbine goes through the condenser, at this constant pressure, it undergoes a change in state from the gaseous, the vapor form, to the liquid form, back to the wet region at 4. Now this entire process takes place in the atmosphere. However, in an actual plant application, right, to improve the thermal efficiency, as I previously mentioned, this liquid condensate is usually pumped back up to the boiler, right? And the cycle is repeat. This is what you call a closed cycle system, right? But as I also mentioned, it's not practical to do this on a small scale system like this, right? So this open cycle ends at 4, right? So for this open cycle, we could see that from 1 to 4, right? In the actual Rankine cycle, it's a closed cycle, and you will see this as you do additional research to produce your lab report, and when you get to this topic later in your course. So now that we have a better understanding of the schematic of the lab apparatus, and we understand how to draw the TSS diagram for the cycle, we have completed objectives 1 and 2 of the lab. We can identify the major components and draw the TSS diagram of the cycle. The third objective is to actually perform the experimental analysis and collect data by actually running the lab apparatus. So let's proceed with that. So now that we understand the basic operating of the Rankine cycle and as it applies to laboratory equipment, we'll actually move on to the system and perform a demonstration. So the first step, as you could see on page 2 of your lab scripts, is to fill the boiler with 600 milliliters of distilled water. The next step, is to remove the filling equipment
ensure that the steam admission valve is closed. Switch on the computer and ensure that it is connected to the equipment. Ensure that the gas valve is in the on position and the gas isolation valve is also in the on position. The next step is to turn on the machinery, and to do this we look at the master switch and we turn the key towards the right, and you can see that the green light comes on. The next step is to flip on the burner switch. See, the red light comes on. You can see that the blower begins to rotate and spin. Now it goes through a gas purging system process before it ignites. So you can see that the blower has been ignited, and it will begin the heating process of the water in the boiler to produce steam. The next step is to verify that the pressure on the boiler pressure gauge approaches steady state conditions. So this will take a couple minutes, so we will return when it approaches steady state. So back on step 12, we will open the steam admission valve. Turn on the load switch and start adjusting the load rheostat to achieve steady state conditions. If you observe the voltmeter, you can see that the generator is actually producing a rectified DC voltage. So you can see we are approaching steady state conditions around 6 volts and 2 amps approximately. So if you could direct our focus to the instrumentation software on the computer, you can see the various parameters: boiler pressure, turbine inlet pressure, turbine outlet pressure, boiler temperature, turbine inlet temperature, and turbine outlet temperature. We also have the ammeter displaying the current, the voltmeter displaying the voltage, as well as the flow rate meter. So these are the thermodynamic properties required for the lab.
So after steady state conditions were achieved in the lab, right, these are some sample data that was collected and presented here. So in the event that we are unable to actually conduct the labs on campus, these are the results you would use to perform your thermodynamic calculations. So in your lab scripts, you would also see some sample data recorded. Right now, this data is really used to go into detail in the lab script on how exactly to perform the required thermodynamic calculations. Right, the script goes into a lot of detail. Right, so I'd encourage you to follow it closely and pay particular attention to the instructions. Right, to be able to perform your calculations. Now, these calculations will be applied to the results presented previously, but in your script, these are just an example to follow closely. right? The first step usually is to determine the enthalpy values at each stage, stage 1 to 4, right? And the script itself gives detailed instructions on how to go about doing this. Now, the main thing that you need to know how to do is how to use your Steam tables, right? So this will be covered in class. So once you absorb that knowledge, you'll be able to apply it to the instructions given in this lab. Just some additional guidelines on how to go about producing a lab report, right? Everything here is pretty much self-explanatory in terms of the layout and the major headings, right? So you start with the cover page. You have information like your course code, your lab title, student ID, etc. Then your title, the title is located at the front of your lab script, so you can just copy it back. Now, at the summary is usually done lastly, right? So after you complete your entire lab report, you perform your calculations, your analysis, all of this, then you briefly summarize in no more than 100 words the contents of the lab report, right? Now you go into the description of your apparatus, you put a brief something on the boiler, the turbine, as the case may be. Um, in the theory section, discuss the theory on which the experiment and the calculations are based. Now, the entire experiment and the calculations are based on the Rankine cycle, right? So, in this section, you would go into discussing the stages of the actual cycle, right? As I mentioned, the cycle in the lab was not fully representative of the actual cycle. So, you could do a little research on that, and produce a well done theory on the actual Rankine cycle, which would be the closed cycle. For your results section, you would make sure to tabulate your results in a neat form, in a neat manner, and present it well. And be sure to include your thermodynamic calculations, right? Typewritten, of course. In your discussion, everything here, have a lot of guidelines on how to go about producing your discussion. So after, you would do analysis in terms of the efficiencies, you calculate, and compare to the actual plant, right? In terms of recommendations, I'll just touch here briefly for a second. Now, in the lab, if you observe closely, you will tend to see some leaks at different points, right? Now, these leaks tend to contribute to erroneous results, errors in results. So that is a major source of error on the lab equipment. Now, these leaks mainly due to the infrequent servicing of the apparatus, right? And that could affect the normal functioning of each component, and this hence reduces the efficiency of the system, right? So to improve this, you would want to implement a more frequent servicing schedule, right? And also, although the steam at the turbine inlet is superheated, as we throttle the steam from the boiler outlet from 1 to 2, right? We throttle the steam and it becomes superheated to enter the turbine. Even though this steam is superheated, right, the apparatus is fairly old, right? Really old, right? And over time, as steam continuously passes through the turbine blades, we tend to have condensation on the blades or the turbine. And now these turbine blades are made out of steel, which is susceptible to corrosion, right? So currently the blades of the turbine is corroded, and this could also, this also reduces the efficiency of the system, right? So if you want to improve the apparatus, one thing you could do is replace the blades of the turbine with a more corrosion resistant material, with like titanium, for example, right? So I just wanted to touch on that to enhance your discussion. Now we also have some additional guidelines for discussion, and number one is how we would improve the thermal efficiency of the cycle demonstration unit without any additional modifications. Now, so one way you could do this is by increasing the pressure at the boiler and reducing the pressure at the condenser, right? And what this would do is would minimize the amount of heat loss from the system to the environment, and this would hence improve the thermal efficiency, right? Now, another way you could do this, you could ensure that the steam leaving the boiler is superheated to a higher temperature, right? So in the cycle, we saw that the steam leaving the boiler was dry saturated, and we needed to throttle it to get to the superheated temperature, right? Now, if we superheat the steam at a higher temperature than what is in the lab, what this will do is reduce the dryness fraction of the steam. Sorry, not reduce, it will increase the dryness fraction of the steam, sorry. And this increase in dryness fraction would mean that the moisture content in the steam is a lot less, right? So if the steam has a lot less moisture in it as it passes through the turbine blades, it will reduce the risk of corrosion on the turbine blades, right? So that's one thing you'll want to do. you want to ensure that the steam leaving the boiler is superheated before it enters, well, superheated to a higher temperature before it enters the turbine, right? Now, how would improve the thermal efficiency of the Rankine cycle if it was possible to include additional modifications, right? As I previously mentioned, one modification you could do is replace the turbine blades with a more corrosion-resistant material, right, such as titanium. And how does this cycle compare to an actual plant cycle, right, in terms of performance and major components? Now, I'll leave this part up to your discretion. You would use your calculated values to produce a properly analyzed discussion for this answer, right? Use your analytical skills in terms of the values and your understanding from additional research to produce a proper discussion in this area, right? One thing I would mention, as I mentioned earlier in the presentation, is that with an actual system, there's a pump which pumps the reclaimed condensate back to the boiler, and that makes the actual systems more efficient, right? After this, you're going to a conclusion, which is very concise, a couple of lines, about 5 maximum, or 5 or 6 lines a paragraph, right? You conclude your main findings at the lab, such as your calculated values or whatnot. You could use your discretion in that sense. I'll leave that up to you, right? The appendix, if you were able to calculate, if you were able to actually perform the lab on campus, then the results recorded on that day would be signed by myself and would be required to be scanned and included in the lab report, right? So that's basically the general process of going about producing a lab report, and that's it for the lab, really and truly. So that brings us to the end of this lab demonstration. Feel free to email me or call or WhatsApp me if you require any additional information, assistance, or you have any questions. Thank you.